Okay, hello everyone. You're very welcome to today's ISESA's webinar, which is entitled Don't Fool Yourself, a practical map to statistical inferences presented by Dr. Joe Warne from Technological University in Dublin. Before we begin, I'd just like to take this moment to congratulate Dr. Adam Granger and his conference committee on an absolutely fantastic and very successful conference at SETU in Waterford last week. It really was a magnificent event. So well done to all those involved, including students, undergrads, postgraduates. The standard of work presented was really top notch and I was very impressed. So congratulations to you all. For those who did attend, can I just take this moment to remind you to complete the post-conference survey, which has been emailed to you, and personally just check your junk box email as well. That's where mine landed to. So if you haven't received that email communication, it may be there. So we'd certainly really appreciate if you could complete that post-conference survey. So on to today's webinar, and today is a first because we are welcoming back a guest speaker for the first time. Dr. Joe Warne joined us in November 2024 with his very thought-provoking webinar entitled Are Scientific Cultures Benefiting Scientific Progress? A talk that highlighted problematic practices around research, robustness, and replication, and so on. Let's just say the feedback from that session was impactful. It was somewhat unsettling for some in terms of the reality of some of the poor practices. But I think it is important that we flag potential issues in relation to that. For those who did miss this webinar, it is available on our YouTube channel. So I would recommend that you also check that out in relation to today's content. So because of the topic that we're talking about, Joe very generously offered to return and to build on that discussion. Today's webinar aims to clarify key statistical concepts and provide a practical roadmap for making transparent, reproducible and robust claims from your data. Before I hand over to Joe, can I please invite our audience members that if you do have a question, now's a great opportunity to contact and to ask, pick Joe's brain. So please use our Q&A function. So without further ado, I'll hand over to Joe. Thanks, Joe.
Thanks so much, and thanks again to ISESA for having me for part two here. We did offer to do this on the basis that, part one was maybe a somewhat negative overview of the discipline in the field. Unfortunately, it is the reality that we're seeing. And the main takeaway point I said is that unfortunately, with the level of replication that we're seeing, you would be more likely to test a theory or to come to a right claim just flipping a coin. And so, in that talk, I didn't actually give any practical insight or guidelines into how one might better improve their statistical inferences, which is why we offered to do this part two. And this is definitely credited not to me. This is heavily as a result of the work by this individual here, Daniel Laken from Technological University Eindhoven, who's been a huge influence on me and our team and is now a strong collaborator with us. I will say, if you're anyway interested in education on all these areas that we're going to talk about, don't listen to me. Go ahead and look at the number of different resources available from Daniel, such as his free Coursera course called Improving Your Statistical Inferences, or his free online textbook, which is called Improve Your Statistical Inferences. And he has very generously made what I consider to be one of the gold standard textbooks of our time in making better inferential estimates free, available online for everyone to use, which is an incredibly generous and well-meaning thing to do for science in general. And this talk was heavily inspired by a point that Daniel makes in one of his videos, which is that when we are talking about error control, and in this case, we're talking about the long run replicability of the claims that we're making in science, the goal is really not to make a fool out of yourself too often in the long run. And by that, what we mean is that we should be, whenever we are testing a specific hypothesis, asking ourselves whether or not we have any confidence in the long run probability of that claim reoccurring again and again and again in the future. Now, Unfortunately, with a 40 plus, maybe 50-minute talk here, I had to cut a huge amount of information out of this. I am very much just going to talk about some of the big hitters. I used this model, the hypothetical deductive model of scientific methods before, and you see in this actually a whole host of things that I would love to be able to go through in detail. And in fact, there's probably about 10 hours of delivery here. So just to note that we are going to hit on some of the main issues and some suggestions of how we can improve practice. And again, I will kind of uh, assume that some people have a working knowledge of things like error control, type 1 and type 2 error, and the basics of null hypothesis testing before we go into this. The goal then for all of us as researchers, if there was the one main guideline I would offer people, is to consider the concept of verisimilitude, which is essentially truth seeking. And that is what we are doing as educated researchers trying to pursue theory. And this particularly applies in the context of testing a hypothesis, which we define as confirmatory research. And it's important to remember within that there are certain limitations around probabilistic estimates that we use, in other words, our probability tests or null hypothesis tests, to make claims about theories. Because very often we see people making overzealous claims or overconfident claims. But it's important to remember that on the basis that this is just a probabilistic estimate in the long run of whether this may or may not support a theory, the claim that we are making is about our data and not actually about the long run probability of a theory holding true. So data never proves a theory. And this is why replication is the gold standard here, because if no one study, this is my golden rule of research, no one study is proof of anything, then we have to consider that within a single study, we need to be careful of our language and considering the likelihood of the observations that we make reoccurring again in the future, taking this meta-science lens to how we both interpret well, plan and interpret our research, but also the language that we use, and which is obviously read by a number of both educated and uneducated individuals in the final published version, in the language that we use in conveying the clarity of the claim that we're making. And most of this relates to this theory that I've talked about before, which we need to make a clear distinction when we're conducting research on whether we're conducting exploratory research or confirmatory research. And one of our concerns is that many researchers in sports and exercise science appear to be using a hybrid model. They don't very clearly define or perhaps understand exactly what a confirmatory study should be. And so this is the first important question for you as the researcher, which is, are you really testing a theory? Is this a very specific, stringent test or a theory or a problem that I am trying to solve, of which I'm going to conduct a very narrow, streamlined, directed study, singularly to interpret this single hypothesis or theory that we would like to investigate? Or am I engaging in a more exploratory model, which is I'm going to test a lot of things, and within this, I'm then going to make some claims about maybe a more global or a more general theory, or indeed, in some cases, people might collect a lot of data and then retrospectively write a hypothesis to fit what they observe. And one of the issues that we have is that people seem to celebrate or want to do more confirmatory work. People like the idea of finding evidence that corroborates a hypothesis. But actually, it's really important that we celebrate the value of this exploratory work. There's a great paper by Anne Scheel which says hypothesis testers should actually spend less time testing hypothesis and engaging in much more theoretically valuable research, just exploring things. And within that, you don't need to define a hypothesis. You don't need to very carefully test a single theory, but instead it is perfectly appropriate to not include a hypothesis whatsoever and just say, we had access to or the opportunity to test a whole load of variables, and we present them here descriptively to you. And they would be presented as an exploratory study or as a preliminary report in the absence of a specific theory of which we are making claims about. Now, this is incredibly valuable for a number of reasons. It helps us to inform future confirmatory research that we would like to do, and we would like to see this done a lot more. But also, it can be very useful in understanding potential effect sizes, which become very important when we're justifying our sample sizes. Very commonly, I'm going to use a couple of examples here of this concern that we have is that we don't believe that many researchers really understand the difference between exploratory research and confirmatory research. And here's an example taken from a research paper of a hypothesis. It was hypothesized that those who participate in a 12-week isometric neck strengthening program will have greater strength improvements compared to those who do not. And so at face level, this seems like a very nice hypothesis. There is a variable that they're measuring, which is neck strength, isometric neck strength, and they are comparing a group with without this 12-week isometric neck strengthening program. So at face level, this seems like a very nice confirmatory study. So the ideal in this case would be that there is now one dependent variable. Isometric neck strength is measured in one way. And then there are two groups, one who engage in the intervention and one who don't, ideally in a randomized control trial. And since they have one dependent variable, we can very easily run a power analysis for this on the basis of this one dependent variable. And we can power the study to control for type 2 error on the basis of this thing that we're doing. And ideally, a hypothesis, since this is a binary outcome, either we find evidence in favor of or in support of our theory, or not in support of our theory. This should be ideally a 1-to-1 ratio. One dependent variable being tested as part of one hypothesis should be interpreted with only a single p-value. And in this case, the p-value of interest would be the interaction. Was there a difference in the response to this 12-week training program in the intervention group when compared to the control? Just the interaction effect is the only thing that we're interested in here. Sorry, it's the interaction, to be clear if I misspoke there. However, the real situation is that it appears that people are engaging in what they call hypothesis-driven confirmatory work, but very, very commonly they're blurring the lines to more exploratory work. And this is, I cannot understate just how prevalent this is in the sports and exercise science, and this presents a real issue and concern for us. Firstly, the term isometric neck strength or strength in the hypothesis was actually an umbrella statement, and it wasn't a single variable. They actually tested 14 different measures of strength within that single hypothesis. Because there's 14, there was no power analysis because you simply cannot feasibly power a study with 14 variables. And they actually reported 42 p-values as part of their results section. So 42 different null hypothesis tests to test this single hypothesis. So you can see here that actually there is somewhat of an exploratory nature to testing a very specific hypothesis. And so in this case, whilst it might be considered a confirmatory study on the basis that a hypothesis is included, this is actually an exploratory study and should be justified as such. So the key message here, and I'll come on to this in a minute, is we need to urgently refine and simplify hypothesis in confirmatory studies. A second example is this one here, which is a little bit busy, but is examining the effects of caffeinated energy drinks in badminton players. And again, they use similar terminology in the yellow highlighted hypothesis statement at the top here. They say we hypothesize that a caffeine-containing energy drink would increase the physical performance during badminton-specific testing and game in elite players. And this would suggest to us that what they're interested in is variables that specifically relate to changes or are correlated with performance in badminton-specific scenarios. And again, they go on, whilst they only state one dependent variable in the hypothesis, physical performance, they actually test this in a huge amount of ways, and I've just summarized some of them in these two tables that you can see here. Within these, we can see that the ones that we might consider, having looked at this, to be badminton-specific, things like smash jump height with and without a shuttlecock, and the total points one, demonstrated no statistical significant effect with respect to the effect of caffeinated energy drink in these 16 badminton players. The ones that did were both squat jump and counter movement jump, which while might be somewhat correlated with badminton performance, are not something that we maybe consider badminton specific. But yet the major conclusion, and probably the most concerning thing and a very prevalent issue that we see, is this opportunistic reporting that takes place when people test a multiplicity of hypothesis statements, as you can see here. They conclude in this study, all this information suggests that caffeinated energy drinks may be an ergogenic aid to increase jump performance and specific movements during badminton. And we do not consider that they have the evidence to support that hypothesis on the basis that the non-specific badminton tests showed statistical significance, and all of the ones that might be specific to badminton did not. And this is a somewhat opportunistic and biased approach to testing what should be a very strict and severe hypothesis. Now, within this, there's also a certain issue with sample size. And of course, that's one of the big concerns that we've discussed around not only sports and exercise science, but of course, the wider social sciences. And of course, within our discipline, sample size is a very feasible constraint because it's very difficult to have access to players and athletes and people to come in and do somewhat quite extensive testing. But we cannot use that as a means to justify poor error rates. And to understand that, I strongly recommend that people get very familiar with these four pillars of null hypothesis testing. You know, again, if my second major recommendation to everyone today as researchers, it is you should be incredibly familiar with things like your type 1 and type 2 error control of the value and the relationship of effect sizes into these error control measures, and how we might therefore go and use that to justify and calculate a sample size. Now, there is a very, very nice visualization available for this on this website that I've linked here, and I'll leave in the notes, and you can see have it up on the screen. And what's important for us to note here is that all four of these pillars, the level of alpha, which is control of type 1 error, the level of beta, or statistical power, which is the control of type 2 error, the sample size in question, and the effect size are all interrelated to one another. And whilst we won't, do a class here on all of these different pillars and the intricacies of them, the most important thing I want you to remember is that the effect size is intricately linked to these other factors. And all of these determine the eventual p-value that you might determine in a null hypothesis test. Because very commonly we see researchers believe that p-values are entirely mutually different, mutually exclusive to an effect size. They have no relation to one another, but nothing could be further from the truth. So effect sizes very much are closely related to the p-value that you observe in your study. And for the purpose of understanding and leading into using effect sizes to justify error control using sample size, let's just remember that as we increase our sample size, my effect size, you see the effect size Cohen's d here at a moderate 0.5. If I increase this to this arbitrary definition of a large effect, one thing that you will see here is the sample size will go down. Larger effects require smaller samples to test. Likewise, if I'm testing something of a very small effect, let me put this at a 0.2 effect size using Cohen's thresholds, you can see that the required sample size in this case is 196. Now, commonly people use effect sizes retrospectively in research, and they use it just to label what the size of an effect is. But actually, if we're concerned about the long-run probability of our findings reoccurring at the minimum level of an effect size that we consider practically important, then actually we should be taking a lot of time to consider effect sizes long before we ever conduct a study. And let me elaborate on that point. This, I'll come back to this. So one of the, I tried to skip ahead, but it's actually just gonna mess up my flow here, so I'm not going to. On the basis that these four pillars are interconnected to one another, alpha, power, effect size, and sample size, it means that we can plug in any three and result in and calculate a fourth one. And in the example of this badminton study, one thing that we might be able to do is run what's called a sensitivity analysis. And we might say, on the basis that we only had access to 16 players, and using G-power here is a very common statistical tool to use a sensitivity analysis, we might determine that the minimum effect size that we could observe that would be statistically significant is a Cohen's d/C of 0.75, so a moderate to large effect. And this is important because it allows us to see, one, whether this study is sufficiently powered to detect the effect sizes that they are claiming within this study, but also whether there's any issues in the use of or interpretation of effect sizes. And in this badminton study, not only was the issue with this questionable practice of what they reported, as I've already mentioned, but actually our sensitivity analysis would suggest that none of these effects for squat and counter movement jump that they found to be statistically significant should have been so, because they should have actually, on the basis of a sample size of 16, only been able to find statistical significance with the effect size greater than 0.75. And that either means that there's been some questionable research practices or p-hacking involved in arriving at these p-values, which is probably less likely than the second point, which is people have misused or misinterpreted their effect sizes. Cohen's d is particularly important and problematic in this case because actually many researchers don't understand that there are many different forms of Cohen's d effect sizes. And so my third suggestion to researchers here is please spend some time to really understand effect sizes with different statistical models and make sure that you can interpret and use the right ones in the right situation. And the most common example that we see of this mistake is people using Cohen's DS, which is the pooled standard deviation for independent samples analysis, when you have two separate or independent groups being compared. And they actually use this Cohen's d effect size for paired or correlated samples. That is when it's the same group compared in two different occasions. And that is what we suspect happened in the case of this badminton study. So in fact, if you use the wrong one, as you can see, I've used exactly the same data here on the left-hand side in the calculator. The Cohen's DZ, the paired samples Cohen's D, is much, much larger than the independent samples Cohen's D, which is being used incorrectly in this case. And so this has dramatic impact on something like a meta-analysis, where we can't actually use the correct effect size to inform the level of the power analysis on the basis that this is a paired or independent samples test. So it's critical that we understand that there are many different effect sizes, not just for t-tests as we see here, but also for ANOVAs and many other statistical designs. And it's really important that we understand the difference between them. So I showed you a couple of examples there of hypotheses that would be considered somewhat vague. And one of the main things that I would like to suggest to researchers today is when you're engaging in confirmatory research, that you have decided that I want to run a study that is confirmatory, the first thing that you need to do prospectively and ideally with a pre-registration is to come up with a very specific severe test of your hypothesis. So on this basis, here are some recommendations from us. You should explicitly name each dependent variable relevant to the theory and avoid these umbrella terms or vague terminology that actually are being tested in a huge amount of different ways, because it makes it very difficult to know whether you are finding support of or not support of the theory if we use these vague or umbrella terms. We should be much more specific in the terminology within these hypothesis statements, and ideally adopt what we call the Peacock model, and I'll give you an example of that in a moment. We should, and this is very, very common for people to overinflate the number of dependent variables that they test within the hypothesis, but best practice is that we should limit this very severely to only the smallest number of variables that might help us inform that hypothesis, and ideally it should be one. Every hypothesis should ideally have a single variable of which you're using to test it in a very severe manner. We should also avoid vague statements about the anticipated direction of our effect. We very commonly see when we code this, and we've coded more than 500 studies on this basis now, that we will see people say, we hypothesize that there will be a difference. And as opposed to, we hypothesize a large positive improvement in. So give a specific direction of the effect that you would like to determine. It also is important that we make it clear within this hypothesis statement what the main effect of interest in our statistical results will be to corroborate our hypothesis. I used the example a moment ago of using an interaction effect for the isometric neck strength example. So in an ideal world, one single hypothesis should be able to be interpreted by one single p-value. It's a binary outcome of which we find evidence for or evidence against data supports or does not support that theory. So this is a very common thing that we observe, that people actually maybe have a quite well-written hypothesis, but actually go ahead and test so many different iterations of the single variable of their data that there's no binary outcome. It's very difficult to make a decision about whether they found evidence in favor of this hypothesis or not. It goes without saying, and this is becoming a mandatory requirement in most journals now, well, not most, but it's improving, that there's a priori power analysis for all of these named dependent variables. If we're really concerned with controlling the level of error in our claims, we absolutely prospectively need to determine what the smallest effect size is of interest to us in the study and include a power analysis to determine the required sample size. And if we do want to engage in this practice of testing lots of dependent variables, which, is not something that we should necessarily be discouraging, it is perfectly acceptable to have a single variable of which you're using to confirm your primary hypothesis. This was the main thing that you prospectively intended to measure, and then list all the other variables as what we call secondary descriptive measures, of which you now don't need to inform a sample size justification for. They can be preliminary or pilot study results, which you can argue whilst you were engaging in the process of collecting this data, you might as well report them here so it can inform future research. That is a far better outcome than testing 10, 20, 30 different variables and trying to interpret them all as part of this single hypothesis. So I mentioned this Peacock model, and apologies, I know I'm moving a little fast here. I've put way too much into this talk. But the Peacock model essentially is a method of us double checking that when we make an aim or hypothesis statement, that we're including all of the relevant information to make this single statement reproducible. Have we carefully defined the population of which this theory is based, the intervention that we intend to, or the manipulation that we intend to apply, the control or the comparative group or condition that we'll be using to compare against, the outcome or the dependent variable or variables which are relevant to this hypothesis, and whether there is any time component that might be relevant here. And in this example, you can see I've worked through it in the case of a caffeine study, and therefore if we put this into a single reproducible hypothesis statement, it might look something like this. We hypothesize a small improvement in jump performance. Specifically named variable is CMJ, height in centimeters, when comparing a 60-minute ingestion of 300 milligrams caffeinated chewing gum and when we compare it to a placebo gum in our population of interest here, female soccer athletes. And what this allows us to do, of course, is to have a single binary statement. There will now be one p-value attached to this test. We will test the difference in CMJ height compared to the caffeine gum condition compared to the placebo gum, and we will be able to make a claim in relation to this hypothesis. And importantly here, what I want to move on to is that we have defined the size of the effect that we deem of importance in the case of this caffeine research. And this is a very theoretical area to move into, but is absolutely essential in moving and progressing our sports and exercise science forward, which is we need to spend much more time theorizing what are the effects that matter to us. In this case, we've said that we would consider a small improvement in CMJ height as a result of caffeine to be something that in the real world would be very applicable and something that would be meaningful. Just chewing some gum, if that had any influence on CMJ height that is reproducible in the future, that is something that we would consider to be worthwhile, and therefore we define it as a very small effect in this case. So what we're asking is, what is the size of the effect of interest? And now this question would allow us to justify and define the sample size that we would need in order to measure this effect of interest. To give you some examples on different ends of the spectrum, a large one might be if we're conducting a study to examine if there is any effect of fatigue, 400-meter race fatigue on jump performance, should say jump performance here. So in this case, if we ask an individual, a number of individuals to run a 400-meter race on a track all out, so completely floored at the end of that 400 meters, and both pre and post, we measured their jump height, then of course we can easily determine that fatigue is going to have a significant and large effect on their jump performance. So this is a good example where we would say fatigue is going to be incredibly influential on their jump performance, and therefore we are hypothesizing a large effect. In fact, that effect in that example would be so big that I suspect that with 2 to 4 individuals, we would have enough confidence to say without question, yes, fatigue does impair your jump performance. And you can see how a small sample size would be justified in that example. Let's consider a very small effect, the effects of red wine on cancer risk. So this is a correlation study. And in this case, we might say, well, there might be some very, very subtle, long-term, either benefits or positives. I don't know enough about cancer and red wine associations to give you a direction here. The effects of red wine on cancer risk. Now, in this case, we can be damn sure that if someone drinks a glass of wine, they're not suddenly going to develop cancer. Or likewise, they're not going to be cured of cancer on the basis of drinking it. So we're talking about an incredibly subtle, but potentially meaningful long-term effect of red wine on cancer risk, whether it's positive or negative. In this example, we would probably need thousands of individuals in order to reliably determine whether or not there is actually any meaningful correlation in this case. So what matters here, and I've given you 2 extremes, is before you engage in your study, these are important questions. What is the smallest effect size that I believe would be practically interpretable and meaningful in the context of my research? And that is what I'm going to use to justify the sample size of the study. Because most commonly, I mentioned, what we see is people engage in a retrospective labeling of effect sizes. And so I've got on screen here an example of a study, and I've got the Cohen's-d thresholds to remind people if they're not familiar with them. And so this is the first study. This states The results identified a statistically significant positive effect of caffeine on counter movement jump height in recreational runners. And the Cohen's DZ, as you can see, if I label it using the Cohen's thresholds, is a small effect. And that might be something that we consider to be very valuable. That's, in this case, a large effect of caffeine, a meaningful effect. I have to move away from these conventional effect sizes that Cohen's use here because they can be a bit misleading. So what I mean by this is a very meaningful effect of caffeine on CMJ performance. So instead of me just saying it was a small effect, we have to consider the real world implication, which is this was never going to be a Cohen's DZ of 1.4. That's practically impossible with the use of caffeine. Now, in this case, at 0.2 is actually a large and important effect of caffeine. In contrast, if I give you a second example and use exactly the same results, but in this case, the results identified statistically significant positive effect of 6 weeks of strength training on CMJ height in runners. In this case, again, we might, most commonly, people just label this, well, this is a small effect. And in this case, you can see that actually the context is very different. This is recreational runners who haven't previously engaged in strength training. They've engaged in 6 weeks of strength training. And we would consider this to be a minimal or a very small or probably not worthwhile improvement in strength in this group of recreational runners. So it's exactly the same effect size, same statistical results here, but an incredibly different interpretation of this. So in fact, our concern is that people, and Cohen very much warned people against doing this when he provided these thresholds. He said, these are only here in the absence of you having any idea of the real meaningful effects in your studies. So, and you can see this is the quote here. These should only be used in recommended if field-specific estimates are unknown. Now, what does this do? Well, it celebrates again the value of exploratory research. Stop trying to test hypothesis. Do more theoretically grounded research, which actually establishes what these effect sizes that would be meaningful are, and then use that to design and construct your confirmatory research. And our research team, Christian Mosquito, who's an outstandingly intelligent individual, I'm lucky to work with him, and Daniel Laken, wrote a great piece on this, and they made 3 key points. They said, first, these Cohen's thresholds are arbitrary. They just define small, medium, and large effects based on standardized effects that are not relevant. And this leads to the labeling of effect sizes, not interpretation of effect sizes. What does that effect size mean in the context of your work? And thirdly, the problem is it doesn't consider the context of the research. As I've just shown you, using exactly the same arbitrary threshold actually means something very different depending on the context. And context matters when it comes to our effect sizes. Now, of course, this matters because what we're leading to is we need to use these effect sizes prospectively to justify the size of the sample that we're interested in. As identified with that visualization tool, if we have larger effects that are of interest to us, we can justify smaller sample sizes and vice versa. Now, Daniel Laken has some fantastic resources on this, and really, without the time to go through all the different ways that we can justify sample size, a general consensus is that we should be using an a priori power analysis. That is, before we conduct the study, we should be identifying what an effect size of interest to us is on the basis that we understand its relation to alpha and beta, and use that to determine what the minimum sample size we need is so that in the long run, we won't fool ourselves, that we are very confident that if we observe an effect which supports our hypothesis, that we can be confident that this is a reproducible effect. And just a quick note here is that we should not be engaging in post hoc power reporting. This is a common fallacy that we see all the time. All you're doing is essentially reporting the p-value in a different way, and it actually doesn't give any meaningful insight into the level of statistical power of your work. So don't report post hoc power. And there's a great paper here, The Abuse of Power by Hennig and Halsey, for anyone who would like to read up on that further. A probably more difficult question, and something I've alluded to here, is how should we actually justify the effect size that we would like to use? What is the effect size that's interesting? And the most commonly used suggestion is the one highlighted here, which is we should use the smallest effect size of interest. What is the smallest effect that is theoretically or practically interesting or relevant in the real world in the context of the research that you're doing? And there's, again, a number of different options here, which we don't have time to go through. And I strongly recommend you read this textbook to look at these in more detail. And this is a difficult and problematic question because it's very difficult for many researchers to spend the time to theorize or really critically think about what this effect size is in the context of the work before they do any work. And again, I want to emphasize, which is why we should be spending less time testing hypotheses, trying to confirm theories, and spending more time doing exploratory theoretical work to develop a boundary of what we know and do not know about effect sizes which matter and do not matter. If we spend more time and celebrate and publish more exploratory work, then that would give us a much better insight into leading to more informed confirmatory work in the future. And this is something that does need a lot of work. Once we've done this and come up with some effort at managing and justifying the smallest effect size, the next thing, of course, is to report this a priori power analysis statement in your paper. And it might look something like this. The G-Power software is used to calculate the required sample size. We use an anticipated effect size of 0.3, significance 0.05, and power, statistical power at 80%. And they identified 17 participants were required. And commonly we see more and more people are engaging in reporting a priori power analysis statements in their work. And this is something should be celebrated. It's a very positive. However, there are still a couple of concerns. The first is that this isn't actually resulting in a meaningful increase in the actual number of participants that people are testing, which I identified in our last talk, and which means people are probably doing this a little bit opportunistically and including it retrospectively to fulfill the requirements of a journal or a reviewer. And secondly, that we found that only 9% of these power statements in our own research is actually reproducible, that we have enough information required in that statement that we can actually reproduce and check that power analysis. So very commonly we see something like this with vague details and no indication of what variable the study is powered for. Remember, we said commonly people test a huge amount of dependent variables. And you can see, whilst this can be applauded that there is a power statement included in this example here, they don't indicate what the statistical model is. Is this a paired samples t-test, an independent samples t-test, an ANOVA, a regression? They don't indicate which dependent variable specifically they powered this effect size at 0.3. There's also no justification of this effect size. Just saying 0.3 is not sufficient. We need to know why you've determined that this is the minimum effect size that you deem important. Most commonly, in fact, what we observed when we coded more than 500 studies and looked at sample size estimates is people use the default settings in G-Power. So in fact, they're not meaningfully powering their study. They are required to include a power analysis. They open up G-Power and they click calculate without actually changing any of the base parameters in there, which of course we know is not good enough. Now, there is some great news here, and this puts more onus on you guys to start to learn and really use this better, including me. I need a lot of work on my own work to improve this, because you have journals like Sports Sciences now coming out with statements like this to make it mandatory that all original studies must include a priori power analysis. And this is just published in the last month by Grant Apt, who's an excellent meta-scientist working with Journal of Sports Scientists. And the good news is it's actually entirely justified on the basis of our work. So you can see that Christian Mosqueda and ourselves wrote a paper published in 2023, which questioned the reproducibility and the merit of the power analysis within the Journal of Sports Sciences. And in fact, we said only 9% of them reported all necessary inputs for us to actually calculate and recheck this power analysis. And so they said that on the basis of our work and their own findings, which they subsequently followed up on, the JSS now believe it's time for sample size estimation and justification to be a mandatory element of original articles. And I just want to take a moment to applaud them for this. This is an incredible step forward for our field and our discipline, because this also, remember, in an industry and a research space where people applaud novelty, this limits the chance of novelty, because if you adequately power your study, you are less likely to find these novel, significant, interesting effects. And so this should be highly applauded from these individuals. And what was really nice about this editorial from Journal of Sports Sciences is they also provided essential sample size estimation reporting guidelines. They said it's not just okay on the basis of that example I've just shown you to give us the minimum details, but actually you need all of these things here included. And again, I'll leave these in the lecture notes, and I'm happy to distribute these afterwards and go through them. They also provide an exemplar. They say this is actually what it should look like. And you can see that there is considerably more detail included here than in the example that we commonly see as that one that I've just shown you. So lots of text on this slide. It might be worth pausing retrospectively and looking through this one. We do have an issue with the Journal of Sports Science recommendation, and we're actually writing a response right now on this, because actually this is kind of a secondary issue, that just including a priori power analysis, which typically is done for one dependent variable, doesn't support what people are actually doing in confirmatory work. And so I've mentioned a really good guideline for everybody in research is, if you're going to test a hypothesis, limit it down, stop testing so many variables. So our data suggests that in the hypothesis statement, people typically name 3 dependent variables, but they proceed at a median, an average, to test about 13 in the results section. And on the median is 64 statistical tests or p-values within that results section to test one hypothesis. Now, in some extremes, we've seen 1,500 statistical tests to test one hypothesis. So you can see how this really blurs the line between confirmatory and exploratory work. So in this case, if you are testing 13 dependent variables on average in your work, you can't justify a sample size calculation for 13 variables. And this fantastic study from Bender and Lange essentially says, well, if you are going to test lots of things, adjusting for multiple testing is actually incredibly difficult and will not allow you to make one final binary conclusion on the basis of your work. So don't use complex statistical designs and don't test a huge amount of dependent variables. In fact, they go on to say that the level of complexity in many of these studies is so high that even these individuals, as experts in multiple corrections, would not be effectively able to control the error in these studies because of the sheer volume of testing that's being done by individuals. So what's the message? Do less. Don't fool yourself here by testing way too many things and struggle to come to a conclusion that you can stand behind when you're either showing evidence in support of or against your hypothesis. So a couple more things here. When it's really important that for everyone who consumes our research, that we make sure that we adopt our language accordingly. So because remember what we said at the start, that this idea of verisimilitude is we're pursuing truth using probability, means that no one study is proof of anything. And if we don't engage in really high-level control of these error rates prospectively with power analysis and carefully considering our level of alpha, etc., then we've no way to determine if this is actually a reproducible or a consistent or a valid finding. So in fact, it might be worth us changing the way in which we, in our conclusion, in our discussion, phrasing whether or not we're finding evidence for or against this hypothesis. And this is a great example from Daniel Laken here again. He says we should probably put right instead the p-value, x, which corroborates our prediction at an alpha level of y, or if it's not statistically significant, the p-value of x, which does not corroborate a prediction at the level of statistical power of y. At the level of our effect size of interest. So in other words, we're changing the terminology to instead say, yes, we are accepting or rejecting, this is evidence or proof of a thing. We're actually saying, well, we're only as certain as our level of error control. That's as sure as we can be. So with this uncertainty in mind, here is what we tentatively suggest on the basis of this hypothesis. I want to make just one more point here. I'm conscious of time and trying to cover too much stuff, which is, and this is a more broad area outside of those factors I've mentioned, around being much more transparent in what we're reporting. There's this dimensions of research quality framework, which essentially says when someone peer reviews our research, it's very easy at a face level to see what someone has presented to you. It's like buying a used car. If you go into a garage and buy a used car, the garage and whoever sells it to you, the salesman who's got all the swanky words, will tell you everything. It's only had one driver, they never sped, it's had a full service history, and you have to take at face value what they're saying. You don't know for sure what the mileage, well, you know the mileage is, but you don't know how the wear and tear or the level of use or the misuse of that car has been. You have to accept this at face value. And so the same is true when we're peer reviewing work. We can evaluate the quality of the reporting within the study. We can evaluate the relevance to policy and practice and this study's impact in the global area of sports and exercise science. And we can evaluate the appropriateness of the methods and the research design. But actually, what we cannot evaluate without some transparency is the underpinning behind the scenes methodological decisions, what we call the researcher's degrees of freedom. So if we do want to make our research more valid in the long run, we need to allow falsification. And to do that, we need transparency. And the best way that we can try to do this is by engaging in pre-registration or registered reports. And this isn't as hard as people think. I've got a link here to As Predicted for you guys just to have a look at. And I'll leave this in the lecture notes. But people believe that pre-registration is incredibly cumbersome and difficult and long-winded. But most of the time, people are engaging in ethical applications. And most of the information that you need for a pre-registration is already included in an ethical application to a university ethics committee. And so actually pre-registering this publicly would be one very positive step forward to making sure that there is transparency in all of these methodological decisions and not waiting to retrospectively present some polished car saying that it's got all of these lovely things that have happened to it without actually showing the track history to do so. And this is just a screenshot of what that would look like in the As Predicted website, because it's particularly of interest to us because it's very short. I use this for my students all the time. If you've got an ethical application done, this is 5 minutes of work. Sorry, Carla, I know I'm slightly over time here. My last, on the same point, talking about transparency, you should consider the FAIR principles. And these are becoming much more popular across all university mandates, which is make your data, your resources, your analysis, findable, accessible, interoperable, and reusable. And one of the main ways that we can do this is by sharing our raw data and our analysis syntax. And again, I've put this together. This is something I consider really valuable work that I've done on giving guidelines to researchers in how they might go about checking whether they can effectively share the data and all of the components there. The last thing that we need to engage in is better reporting of our statistical information. Very commonly, we see a statement like this. People say there was no difference and provide a p-value and then the descriptive statistics. And this is not enough for us to reproduce or validate or replicate this work. On the basis of transparency, we should be including all of our parametric assumptions information, whether we had normality, whether it failed, how we dealt with outliers, all of the decisions that we made that were incredibly important that led to us making a claim at the end, and then including all of the APA required formats and guidelines for our reporting practices, including, in this case, the mean difference, the confidence interval of the difference, the p-value, the Cohen's d, the correct effect size, the confidence interval of this effect size, the degrees of freedom, the t-value, and the correlation of this is paired measures. So all of this should always be reported to facilitate reproducibility in this work. So sorry, that was a whistle-stop tour through some of the key things that we need to be considering when we're engaging in research. Again, just to thank, this work is not mine. I can credit to these incredibly intelligent people you see on the screen here. And thanks again for tuning in.
Okay, thank you so much, Joe. That was excellent, really interesting. I certainly have questions, but I'm going to defer to the audience in the first case. So, first question is, in practice, we often want to determine if there has been a meaningful change in an individual athlete's test score. Are there any approaches you would recommend to do this? For instance, smallest worthwhile change, Z score, modified Z score, etc.
Yeah, it's a great question. And this is an entirely separate area, right? Because on the base of everything that we've discussed, we're really talking about probability assessments and using null hypothesis testing to test hypothesis. When you're dealing with individual athletes, of course, you can get much more meaningful insight from things like an individual response, which wouldn't necessarily be that relevant to mean tests of differences as we've discussed. But actually, the things that you've recommended are exactly what I would recommend, something like Z-score profiling and understanding. The same questions apply here on a theoretical basis, whether you're working with an individual athlete or whether you're working with group means and looking at hypothesis tests, which is what matters. Like, how much of an effect would you be happy to see on that basis? And if you talk to really high level coaches in a sport, they will tell you, if I do this intervention with a beginner athlete, I expect or would be happy to see this much of a change. So it's a much more theoretical question. And I think we don't necessarily always have to fall back on what's the most appropriate statistics, but first engage in that theoretical question of what matters to us, and it depends on how much resources you've invested, how much time they've been involved, their own training status, their own learning curve. If you're working with a novice versus a very experienced athlete, you're going to have very different responses in that case. So by just using for example, a Z-score of anything above 1 standard deviation might be very relevant and meaningful in novice athletes where you're going to see significant changes, in just small amounts of training. But if you're working with an elite athlete at the latter end of their career, something like a change of a Z-score of 0.1, 0.2 might be career changing. It might be a difference between an Olympic medal and not an Olympic medal. So that's the most important underlying message, I think, across all of this area, which is first, become a philosopher of science. Ask what matters here. And then secondly, find what best statistics and numbers can suit what what you want to examine.
Okay. I suppose probably related to that question and your response, I'm just going to skip down to a similar type question and you might say a similar answer. Really interesting presentation. What would you suggest for statistical inferences in elite populations when sample sizes tend to be small, or an example of a case study of an n is equal to 1?
Yeah, well, you wouldn't use statistical inferences in that case. It's all around the claims that you're making. If a statistical inference like that is making a claim in the long run on the basis that you can be confident that you are controlling adequately for error. So if I claim that there is a statistically significant effect, I need to be confident that that is true, that what that claim I've made is true. And if we're dealing with sample sizes that don't allow us to adequately control for that level of error, which is perfectly fine and should be acceptable part of practice, we need to instead change the way in which we approach it. We cannot make a claim. We cannot say we are accepting or rejecting a hypothesis or finding support or evidence against. And so you would instead change your terminology to maybe say, and I know Journal of Science and Medicine and Football have this new category now, they call it preliminary reports. So in the case where you cannot justify your sample size, or your sample size is simply too large to be feasible, you would submit it as a preliminary report, and you would not be allowed in the discussion section to make a binary claim about what you've observed. So it's all around understanding when this is appropriate to use and if we should use it. And in cases where elite athletes and using very small samples is very valuable information, we might not necessarily be testing hypothesis. We just want to descriptively say we have limited access to these 10 world-class individuals. Given the limited sample size and the small effect that we're interested in, we're going to report this descriptively. And we're not going to make a claim that is falsifiable.
That's really interesting. So something like percentage of change
Exactly.
might
Yeah.
be suffice in that
And,
case.
and and I mentioned there like the difference between exploratory and confirmatory work because
Mm.
that would be incredibly valuable for someone in the future who now has the resources to test an elite population and test a specific theory. And they can say in some preliminary work by Ryan et al., when they had access to 7 world-class endurance athletes, they observed a mean change of or a change of 2.5% in this variable. And they can say on the basis of that preliminary report, we can now use that to inform the effect size that we consider relevant, that we want to now test and confirm in follow-on work. So it's a really nice example of how those two things are very much interrelated and both very valuable. But yet everyone wants to publish a confirmatory study that finds proof of their hypothesis, right? And we need to maybe stop celebrating that as much and just accept that sometimes in our discipline, large sample sizes is nigh on impossible. And if that means that we have very limited confidence in our claims, then so be it. But we should make that very clear.
Yeah. Okay, super. Thanks very much for your thoughts on that. In exploratory work, how should we speak about significant findings? Report them as significant, discuss their potential implications, and then acknowledge that these are exploratory and the potential for type 1 errors from you get me,
Simplicity.
was not controlled.
Yeah, I think it's the same answer to the last question, right? Which is the most important thing, if anyone can take away from this talk, is just be transparent. Identify
Mm.
these limitations in what you're doing. And in exploratory work, using statistical tests is absolutely appropriate on the basis that you adequately control for inflation of type 1 error, right? So if you are going, this is particularly true, by the way, in biomechanics studies. My original area is biomechanics. And you might have someone come into a motion analysis lab and you strap on a load of markers and you measure 50 different variables within the same movement. So in that case, if you want to report that as an exploratory study, where there might possibly be some interesting trends or things that might be interesting to follow up later in confirmatory work, then it's very important that we control adequately for type 1 error inflation, which is something like, at the most base level, this is a Bonferroni correction or a Holm correction. It's much more loaded than that because actually it depends on a number of ways in which you plan your work. But in general, my answer is you should tone down your language, report it as preliminary exploratory work, say we're not making any claims, we might have observed of the 40 things that we measured, there were 4 statistically significant p-values even after we corrected for type 1 error inflation, and therefore we present these as things that should be confirmed in the future. You know what I mean? You can't make a claim which is, oh, we have found evidence that this thing exists because we cherry pick these out of a big pile of studies. That's exactly the value of exploratory work because it leads to, okay, in that last study, these four things were potentially of interest. So
Mm.
now let's design a study that singly looks at each one of these in isolation. And now you get a good answer.
Okay, great. Um, we have time for more questions. This is the last one in the inbox so far. If your estimated sample size is much larger than what is feasible or realistic, is it still worth proceeding with the proposed study?
Yeah, look, we should never discourage people from doing research. And I think it comes back to the same point I've made, which is all data, all insight is valuable, even if it just means informing someone's future work. What matters if you know that you haven't got the sample size to have confidence in your claims, that you haven't adequately controlled your error rates, that again, your language in your discussion or in your claims is reflective of that. So again, we might report in a study, we wanted to test a very small effect. We had limited resources or time constraints or access to individuals. Therefore, we only had 30 individuals when actually our sample size said we needed 200. And therefore, we consider this a preliminary investigation
Mm.
of which, again, future work should engage in. Now, there's a second thing that really should be emphasized here. I mentioned the value of data sharing, but what we should be able to do, if things were very transparent, is do what we call individual data meta-analysis, an IPD meta-analysis. So, which is if there was actually enough of these individual small exploratory studies done, that in the future we could actually combine each individual data point, assuming that these had been shared, into one very large study, what's called an IPD meta-analysis. So this would actually still inform us in the long run about potential trends by combining all these studies together and controlling for homogeneity or heterogeneity. And so there's value still in that. So information
Mm.
is information. As long as it's shared with goodwill and free from bias, there is always value in doing studies that are underpowered, assuming that we just don't make very bold claims about,
Mm.
things that are maybe not reproducible.
Okay, and how open are reviewers and editors to exploratory work?
Um, I don't know. Actually, it's a good question. It's definitely underrepresented massively in the literature body. And I think, again, that's both a product of significance bias and publication bias, which is a function of journals trying to
Mm.
prioritize novel, significant findings, which we've discussed as a problem before.
Okay.
But also, researchers also like to, no matter how much, I see this observed phenomenon with my students all the time. I mean, I hammer into them that if you find a non-significant result, it's just as valuable as finding a significant one, because it means that there's no evidence for that theory, and
Mhm.
that's as important as finding evidence for. But I think it's human nature that we want to find something. And still, even in year four, I get students who don't find a statistically significant result and they express disappointment. Oh,
Mhm.
that's a shame. I really wish I had. I'm sure you've seen the same thing. And
Yeah.
so, and it's just human nature that we kind of want to, I don't want to use the word prove, but we want to prove something, right? We want to show that we've contributed something to a theory. And so I think even on a researcher's level, there's less value placed on this exploratory work in the philosophy and in the theoretical underpinnings of developing ideas, as opposed to people just want to jump to the end point, which is I just want to test the fun stuff. So I think the answer is they're not as open as they should be, but it's also a product of they're probably not receiving as many as they should either.
We're starting to run out of time. I just have a brief question or advice, perhaps, is I don't think that we as scientists are being intentionally misleading with how we are doing practice, whatever that might be. And so it seems to me from your two talks now that it's almost there's an education piece across
Yes.
the board. What would your advice be to either institutions or researchers? It might even be in terms of going back to the basics, or how do we go back to the basics if there is a fundamental misunderstanding of even type 1, type 2 error, for example? What's your kind of general advice to kind of upskill ourselves in terms of being good practice out with of what you've spoken about today in terms of sample size and so on?
It's a fantastic observation and something that we've definitely seen as well. And it's probably the biggest concern is there doesn't appear to be the level of education through that undergraduate and postgraduate
Mm.
pathway, which leads people to be researchers, right? And it's actually
Yeah.
something I'm going to pitch for PhD funding for next year to really explore this. And you're right. I think it comes back to the basics. I mean, one thing that comes to mind is Daniel Laken's constantly. People say he's a revolutionary. The stuff he's doing is futuristic, and he says no. Like in in the 1700s, people established that this stuff was important. It was the fundamentals. If you're going to do science, then this was the basics. You needed to understand if you're going to test a p-value, you need to understand level of alpha. He says actually this is the fundamentals that everyone should know at a basic level. And I think my concern is, and certainly my own reflection as well, and for the majority of people that I've talked to on this, which is at undergraduate level in particular, we don't emphasize or celebrate the value of science enough. We typically see that there's one module in research methods and statistics kind of grouped in together. No one really wants to do it. Students don't appreciate the value of it at that point. And also, in my experience, many times it kind of is offset onto lecturers who maybe aren't that keen on delivering it too. And we don't have dedicated people who really want to push this forward. So I think there's a need for an entire revision of our development pathways. I've called this like the research and development pathway. It's a model that I want to roll out in the future, which is what are the things that you need to know when you finish an undergraduate degree? And then what are the things that you need to know when you do a postgraduate degree if you want to be a researcher? Like it's like minimum qualifications, essentially. But I completely agree. I think we have a lot to do on the educational front here.
Yeah. Joe, sadly, we are out of time. I've got a feeling there could be a third appearance, so hopefully. But I
Great.
just want to thank you very much for your time and your efforts today. I know people are starting to leave us to return to their duties after lunch. So thank you to everyone who joined us. Just a very quick heads up, our next webinar takes place on the 26th of June at 12 p.m., which will also feature a returning speaker. That's Professor Kate Pumpa, who will introduce the newly launched ISESA Accredited Sport and Exercise Science designation set to open in October 2025. So make sure to tune into that on the 26th of June. Everyone, enjoy the rest of your day. Thank you again so much, Joe, and speak to you in the next time. All the
Thanks,
best.
guys. Thanks for having me.
Bye bye.